This is the 13th lecture of the course MTH 204A for section B. Recall that in the last lecture we are considering the orbits and stabilizers of the action of a group on itself by conjugation. So, let G be a group and acting on itself by conjugation, then for any x, its orbit is called the conjugacy class of that element x. So, in this lecture we first see the conjugacy classes and stabilizers in the concrete groups, symmetric concrete groups like symmetric group, alternating group and dihydral group. So, let n be n be a natural number. So, we can consider the action of Sn on itself by conjugation. So, we have already observed that if A1 up to AR is a cycle R cycle, then for any tau belonging to Sn, this is nothing but the following R cycle. Okay. This happens always. So, the conjugation, so for an R cycle, its conjugacy classes consists of all R cycles, or its conjugacy classes consists of all R cycles, because if you take any other R cycle, it is easy to construct tau sending each AI to that. So, what I mean is you can easily see that for any R cycle A1 up to AR is a conjugate of this standard R cycle, because sending I to AI and then extending that to all over 1 up to n, we can construct a permutation tau. So, the conjugacy class of any cycle is precisely the set of all cycles of that order. In fact, this enables us to see something even for any general permutation. So, let sigma belong to Sn and let us write sigma as sigma 1 up to sigma k, where these are the disjoint disjoint cycles. Now, for any tau sigma tau inverse is easily seen to be sigma. Okay. Now, for each, so since each sigma is a cycle, so its conjugate is going to be a cycle of the same length, right. So, what does that tell us? It says that for sigma and since sigmas are disjoint, so these are also mutually disjoint, right, because since sigma 1 up to sigma k are disjoint, and as we have already proved that every permutation can be written as a product of disjoint cycles in a unique way, except the order in which the factors occur. So, from that we can say that this is also, so this is nothing but the cycle decomposition of the conjugate tau sigma tau inverse. So, from the cycle decomposition of sigma we can obtain the cycle decomposition of any conjugate of sigma, right. And what does that say? That since the length of each sigma I and tau sigma I tau sigma I tau inverse, since they are same, from that we can, what we can say is for any r from 1 up to n, number of R cycles is same, right, in the cycle decompositions of sigma and any conjugate of sigma, okay. So, for any R, the number of R cycles appearing in the cycle decomposition of sigma is same as the number of R cycles appearing in any conjugate of sigma. So, if this happens, that is for two cycles, that is for two permutations, let us say sigma and sigma prime, if in their cycle decompositions corresponding to every R we have same number of R cycles, then we say that those permutations sigma and sigma prime are of same cycle type. So, that is what we have proved is given any sigma, its conjugacy class consists of, so in its conjugacy class all the elements lying in its conjugacy class are of same cycle type with sigma. Okay. So, I repeat, so for any sigma prime belonging to its conjugacy class should be of the same cycle type with sigma. Conversely, in fact I should lay since this is a straightforward one, I should leave it as an exercise that if sigma and sigma prime are of same cycle type, then sigma prime must be in the conjugacy class of sigma. So, earlier what we have seen is if sigma prime is a conjugate of sigma, then they have sigma prime and sigma are of same cycle type. Now, this exercise says that if they are of the same cycle, sigma prime has same cycle type with that of sigma, then sigma prime must be a conjugate of sigma. That is actually quite easy to see, because let me give you just a quick hint. Maybe here I can put, so let this be the tau 1 up to tau k, let this be the cycle decompositions of sigma prime, and for sigma, since they are the same cycle type, it is quite clear that it can also be written as follows, that some sigma 1 up to sigma k, and you can order this factors in such a way that length of each sigma is equal to length of each tau I. That we can do because they are of the same cycle type. Now the rest is quite obvious thing, how to construct a permutation tau such that sigma tau sigma inverse will be exactly sigma prime. Okay. So, as a quick hint, what you can do is if sigma 1 is of this form, let us say a1 up to let us say a1 k1, and this if tau 1 is equals to some b11 up to b1 k1, then the tau that we are going to consider should send each aij to bij. So, for each cycle, because the way we have arranged the factors, each tau I and sigma I, they have the same order, so we can put a bijection. So, you can put a bijection in such a way that so the corresponding elements in cycle, so for each cycle its corresponding element goes to the corresponding element of the same cycle, and of course apart from these cycles there should be so the number of fixed points in by sigma, number of fixed points by sigma prime, they are also same, and then we can also, since they are in same in number, we can also map them one to one fashion. That is how we get a bijection, we get a permutation such that once if we consider the, so if we consider the conjugate of sigma with that permutation, we get sigma prime. So, I leave the details to you. So, thus inside SN we have characterized all the conjugacy classes. So, namely each conjugacy class consists of precisely all elements having the same cycle type. Thus, number of conjugacy classes in SN is same as number of ways n can be partitioned into positive integers. So, by this what I mean is number of way one can write n equal to n1 up to nk, where each ni is a positive integer and k is also a positive integer, k now is not necessarily fixed. So, number of ways n can be partitioned into positive integers, then for each because for each such partition we will have a, because each such partition uniquely determine a conjugacy class where the cycle type is precisely given by these ni's. Okay. So this gives us the conjugacy classes in Sn. Now it is natural to ask for the conjugacy classes in An. For An, situations become somewhat one needs to work more. So suppose a sigma and sigma prime are in An. So first of all, if they are in the same conjugacy class, then they must have same cycle type, okay, that is quite clear. However, the question is, if they have same cycle type, whether they are conjugate inside An or not. So what we do is, so we consider two cases. So we first fix some sigma, let me do it. So fix sigma whose conjugacy class inside An I am going to talk about. So fix some sigma. So case 1, there is no odd permutation alpha. Okay, I think, okay, let me do this in this way, that there exists an odd permutation alpha such that alpha sigma alpha inverse is sigma. So there is an odd permutation that commutes with sigma. If this is the case, then what we can do is, for any sigma prime belonging to An of same cycle type, with sigma, so since they are of the same cycle type, we know that there exist. So I am getting inside Sn. So there exists tau in Sn such that sigma prime is tau sigma tau inverse, okay, that we can have inside. So both sigma prime and sigma inside Sn. So since they are of the same cycle type, I know that they will be in the same conjugacy class inside Sn. I am not sure whether they will be in the same conjugacy class inside An or not, but that will happen in this case because of the following. So if this tau happens to be even, then we are done. If not, then we can simply replace tau is even, we are done. If tau is odd, then what we can do, we can replace tau by tau times alpha, and it is easy to see that tau times alpha sigma alpha inverse tau inverse. From this it is exactly becomes sigma. So thus what we have seen is, if there is an odd permutation that commutes with sigma, then the conjugacy class of sigma inside Sn is same as the conjugacy class of sigma inside An. That is what we have seen. So if two even permutations, they are inside, if two even permutations so if of course if anything if sigma is even, then any conjugate of that must be an even permutation, that is quite clear. Now the point is, if there is no alpha, then if there is an alpha, then two elements sigma and sigma prime can be conjugated, they are conjugate over Sn, that is same as saying they are conjugate in An as well. So they have the same conjugacy class. Now let us consider the complementary situation. Okay. So what is the complementary situation? That is where there is no odd permutation that commutes with sigma. So permutation is commuting with sigma, that means it has to do in centralizer of that. So therefore in the complementary cases, centralizer of sigma inside An is centralizer of sigma inside Sn, okay, because beyond An there is no odd permutation which is in the centralizer of that is quite clear. If this is the case, then one thing is very immediately clear to us, that the conjugacy class of Sn, what is the order of the conjugacy class? So Sn by the order of the centralizer, okay. Now we can see that is nothing but 2 times an, and this can be resolved as Can. Therefore, what and so that is 2 times exactly order of the conjugacy class of. So, one thing is clear that if this happens, then the length of the conjugacy class inside the order of the conjugacy class inside An will be just half of the conjugacy class inside Sn, conjugacy class inside Sn. So, let us see whether we, I mean, at least we know that this one. So, one thing is clear that again let me try to explain. Let me try to explain to you what is happening. So, like one thing is quite clear that conjugacy class of this is contained inside. This is clear, and now here we see in this case this has half length. So, it is very natural to ask that what is there in the rest half. So, let us see. So, what is this? This is in fact the collection of all of this form, right. Now, we can decompose that into 2 further subsets. And okay, yeah, okay. For the time being, just write. Let's write union. The disjointness will be automatic. Okay, fine. Now, as I said, this will be disjoint because. So, what is this? This is nothing but sigma. So, this is written as a union of this and that, and this is exactly half length with this. So, therefore, this must be the rest half, this must be the rest half, and this union, then there cannot be any overlap. So, therefore, this union must be disjoint union. Now, let us see whether we can have some better description for that or not. Now, what we do is that we rewrite this as follows, that is so again let me remind you that Sn is nothing but the disjoint union of, so is the right coset by the transposition A2. Therefore, we see that in fact this can be written as follows. In fact, that is what the definition is. Okay. So, if this is the case, then in view of that one can write this in the following way. So, thus this is nothing but the, so now the, okay. So, that is how in this case the conjugacy class of Sn splits. It basically it splits into 2 halves. In one half it is nothing but the conjugacy class of sigma inside An, and on the other half is conjugacy class of sigma conjugated by some transposition. Here 1 2 is not at all important, some transposition, and this is going to, and for this even permutation this is going to be the, and for the, yeah, the conjugacy class of this even permutation inside An. So, this and this, their disjoint union is the conjugacy original conjugacy class of sigma inside Sn. So, that is how the conjugacy class decomposes. Okay. Now, for dihedral group I would like to leave it as an exercise, that find all the conjugacy classes in dihedral group. That is interesting. These things it is better if you do it yourself, because that is, then we will have a feel for it how to work with that, and of course this is something which we will be using later on. So, find conjugacy classes in D to N. All right. Yeah. Now, like earlier we have seen that the whenever G acts on a set X, then that action induces an action on the power set. So we will so in this situation, that is the action by conjugation, we will obtain a, so this gives rise to an action of G on the power set of G. How is that action defined? G comma A, where A is a subset of G, is maps to this G A G inverse, that is right. So G acts on power set of G, and now since under this action it is legitimate to talk about the stabilizers. So for every A in for every subset A of G, the stabilizer of A, which is nothing but the collection of all G such that G A G inverse is A. Okay. So in this situation the stabilizer is called the normalizer of A in G. Normalizer of A in G, the notation for that is N G A. Okay. So this is for any A. In particular, when A is a subgroup, then when A is a subgroup, so if H is a subgroup of G, then of course we can talk about its normalizer. So this normalizer, for every G lying in this normalizer, G A G inverse will be G. For every G lying in the normalizer, G A G inverse will be G. So that means H has to be normal inside NGH. Furthermore, if N is a subgroup of G such that H is a normal subgroup of N, then we can immediately see that for every X lying in N, we must have X H X inverse H, which shows that X must be inside the normalizer. So what does these two things show together? They show that given any group G and a subgroup H, the normalizer of the subgroup is the largest subgroup of G in which the given H is normal. Because H is normal in the normalizer, and if H is normal in any other subgroup of G, then that subgroup N must be contained inside the normalizer. So given any G, this is the normalizer is the maximum largest subgroup of G that contains H, and H is normal in largest subgroup of G that contains H as a normal subgroup. Okay, then like previous, so for any A in G, its normalizer, so we can immediately have a normalizer of, we can immediately have the action of Ng on A, because for what is the action here, goes to G A G inverse. Okay. So look at the definition of the normalizer from which it will be clear that why this is inside A, because A is closed under the conjugation by G for every G in the normalizer. So normalizer of a set A acts on the set A, and the kernel of this action, so the kernel of this action, consists of all G in the normalizer. So in fact normalizer such that for every A in A, G A G inverse will be A. So I mean since this is the condition, so saying G is in G such that these holes are G is in normalizer such that these holes are the same thing, and yeah, so which this is the all the group elements which fixes all elements in A by conjugation. So this has a name, this is called the centralizer of A in G. So, remember that earlier we defined centralizer for any element of G. Now, we have extended that to any subset of G, okay. And in particular when A is singleton, then for singleton A is the notion of centralizer of the singleton A is same as the notion of the centralizer of the element A in G. Okay. So, enough of actions by conjugation. Now, let us look at the, now let us find the orbits of some other actions. So, we now consider the action of Gl2c and its subgroups on the Riemann sphere. So, we have Gl2c which acts on C hat by Mobius transformations. Okay. Now, what are the orbits under this action? Let us see that for every A in C, A minus 1, 1, 1, this is a matrix having determinant 1. So, this is in a rectangular SL2C and applying infinity to that, we obtain A, right. So, thus this in fact shows that SL2C, so try to see that so is an SL2C matrix. So, with the help of some SL2C matrix you can bring infinity to any complex number. So, that means it shows SL2C acts on C hat transitively, okay. Since SL2C acts, automatically GL2C also, the action of GL2C also has to be transitive, because a subgroup of that is acting transitively, okay. Now, inside SL2C we have SL2R, inside SL2C we have SL2R. So, let us look at the orbits once we restrict this action to the subgroup SL2R. So, let us observe that if x plus Iy, let Z be x plus Iy with y positive, then we can consider this matrix y 0 x by y and 1 by y. So, this applied on I, what will be the case? I plus x Cz plus d, okay, and them now multiplying by root on the left on the numerator and denominator, we see that this is exactly x plus Iy. So, what do we see pictorially? Pictorially, let us say this is the complex plane, this is the part where imaginary z is 0, okay. We see that this I, by applying SL2R matrices, this I can be brought to any other point in the upper half plane, okay. Similarly, one can show that minus I can be brought to any other point in the lower half plane. So, therefore, this is one orbit, this is another orbit. Now, this shows that the infinity can be brought to any other point on the real axis. Therefore, under the action of SL2R on H2 on this upper half plane, the orbits are we exactly have 3 orbits. One orbit is the upper half plane itself, the another orbit is the lower half plane, which is nothing but the conjugate, a complex conjugate of the upper half plane, and the last one is R union infinity. We have exactly 3 orbits under this action. Okay, now let us concentrate upon this example, and since already we have seen that this action has plus minus identity, the subgroup is in the kernel. So, we can further quotient this group and then safely consider the action of PSL2R on upper half plane, okay. So, in this action, so already we have said that this action is transitive. because I can be sent to any other complex number in the upper half plane, so it is the stabilizer of I. So if A, B, C, D stabilizes I, then we must have, so if A, B, C, D stabilizes I, we must have AI plus B equal to Ci plus D. Then further calculation of course tells us that if we bring it to that side, A equal to D and B equal to minus C, and immediately one can check in this situation AD minus BC will be AD minus BC will be nothing but so the determinant 1, right, is in PSL2R. So this becomes A square plus B square equal to 1, and immediately that is exactly same as C square plus D square, and of course one can check AD plus BC is equals to, in this situation it becomes 0. Therefore this matrix, it's a, so try to see, so this and this two assures that this matrix is orthogonal, okay, orthogonal matrix with determinant 1. So therefore stabilizer of I is, stabilizer of I inside PSL2R is PSO2R, that is nothing but SO2R plus minus I2. If instead of PSL2R, if you would have considered SL2R, then the determinant yeah, so then this would also be included there. Yeah. So then, yeah, so if instead of PSL2 if you would have considered SL2, then the stabilizer would be just SO2. Okay, but we do caution because in this action these are not going to make any effect, so it is better to in a sense remove them. Okay. So thus in this situation the action is transitive and the stabilizer is the PSO2. Now also recall that the action of PSL2 on upper half plane from this action, that yields an action of this PSL2 on the unit tangent bundle of the upper half plane. Unit tangent bundle of the upper half plane. So the question, what about this action? Is this action transitive? Let us try to see. So let this be a vector in the unit tangent bundle, and of course one has I comma I. This is of course a unit vector in the tangent bundle. So in order to show this action is transitive, we have to show that there exists a matrix G, there is a matrix G such that this sends this pair to this pair, okay, that would be enough. Now how to do that? So recall that this action is transitive, right, hence given any z comma v, the z comma v can be sent to some point, can be sent to a point like this by some group element by some G in PSL2R, because the there is a matrix that sends G to I, this Z to I. So if we act by that element, then of course this base point changes to this and this changes to something which is denoted by V prime. So thus we see, thus if we can show that every vector in the unit tangent bundle of this form can be reached from this I comma I, then it will be done, because any z comma v can be sent to a vector like, can be sent to a point in the unit tangent bundle of this form. If you can show that any point of this form can be reached from this I comma I, then it will be done. So therefore which we will do now. So for the simplification notation, now let me drop the prime from the thing. Okay. So now I want a matrix such that, a matrix G such that when it acts on I comma I, we must obtain I comma V. So let us do that for any V. Let V in V let V in C. Okay. So, if we remember the action here, so what is the action, how is that? It just becomes Gi and then 1 plus Cz plus D whole square times I, that is how it is defined. Okay. So, and if this is to be equal to this, then G must come from the stabilizer of I. Now, we know the stabilizer of I is nothing but PSO2R. So, therefore, G can be written, G must be of this form. So, what is G? So, G is nothing but plus minus some orthogonal matrix with determinant 1. So, how does orthogonal matrix 2 by 2 matrix with determinant 1 look like? So, it looks like cos theta sin theta minus sin theta cos theta. Okay. Just so this G will be up to plus minus sign. This is the matrix, and let us see how it acts on I comma I. How it acts on I comma I, then it just becomes of course this one, the base point will be I itself, and here it will be I by cos theta plus I sin theta whole square, cos theta plus I sin theta whole square, right. And then we can further see that we can push this in the numerator, and then we see that this is what we are happening, that cos 2 theta minus sin 2 theta. So, it will be just so cos theta minus I sin theta is going to be its conjugate times I. So, therefore, by opening it up we say it is cos 2 theta minus I sin 2 theta. That is what we are going to have times I. Okay. Yeah. Okay. Let me just do it better way. So, just concentrate on this second one. So, cos theta minus I sin theta square I. So, this is what we can see immediately, cos 2 theta minus I sin 2 theta times I. So, basically sin 2 theta plus I cos 2 theta. Okay. Fine. Now, we see that we have to reach V. So, V is a unit vector in the, V is a unit, so this is a, right, unit is a unit vector in the tangent space at I, and the way this unit vector, this inner product is defined from here it is clear that the V is a complex number with the usual absolute value 1. Hence, from the polar form V must look like some cos theta, some cos phi plus I sin phi. Yeah, so cos phi plus I sin phi. Okay. So, from this description of V, you know that by having a suitable choice for theta, we can make this quantity V. Okay. The further details I am leaving to you. So, this shows that this action is also transitive, and furthermore, once the action is transitive, we should look for the stabilizer, because then by Orbi's stabilizer theorem we see that the G space is isomorphic to some quotient of G. So, here what is the stabilizer of this point I comma I? What is the stabilizer of I comma I? So, of course, the stabilizer has to be of this form for some theta, and if for this theta this also becomes exactly same as I. So, if for some theta, so the first, so of course it is going to preserve, it is going to fix I. Now, the way it acts on the second component, this is what we have. If that is also I, so that means sin 2 theta has to be 0 and cos 2 theta has to be 1. So, if G is in the stabilizer of I comma I, then one must have sin 2 theta 0 and cos 2 theta equal to 0 and cos 2 theta equal to 1, and from here it follows, I am leaving the verification to you. So, from here it follows that for which for G we have only two possibilities, that is exactly. So, if G is a matrix, if G is a matrix of this form, then it has to be either plus identity or minus identity. Inside PSL2 they seem both of them contribute just the identity element. So, thus we see that stabilizer of, that you can understand, if a matrix stabilizes I comma I, from that we have seen that it has only two choice, plus minus identity. Now coming inside PSL2, that becomes the identity element of PSL2. So, stabilizer of PSL2, stabilizer of I comma I in the PSL2R is just the trivial. And as a result of that, so from the isomorphism of G spaces, it follows that PSL2R has a natural bijective mapping with this unit tangent bundle. So, let me again repeat that since the stabilizer is trivial, now the action of PSL2R on this unit tangent bundle, which is defined in a very complicated way. So, after all this we see that there is nothing but, algebraically speaking, nothing but the action of PSL2R on that group by left multiplication and nothing else. I repeat that this unit tangent bundle is defined from a very geometric approach by defining inner product, norm. So, it is a relatively complicated object, and the action of that is also by means of derivative, that is also quite complicated. But after looking at stabilizer and everything, so now this complicated PSL2R space just becomes the group itself, on which the group itself and the action this action is nothing but, and by means of isomorphism, after isomorphism the action is nothing but the left multiplication of PSL2R on itself. Okay. And this identification has several advantages. So, first advantage is from now on we can simply view every unit tangent vector by some matrix, and by means of this also we do have a group structure on T1H. If we do not get, had we been completely unaware of such this identification, we cannot even think of a natural group structure on T1H. But by means of this identification we do have. Similarly, we can topologize this by having a topology on here, which is the quotient topology. Similarly, we can put a measure here. So, all these things we can do, I am sure you will encounter them later. But the important part is that this has this PSL2R space is up to isomorphism nothing but the PSL2R, I mean the action nothing but PSL2R, when the group itself is acting on that by left multiplication. Anyway, so do I need to say anything? Yeah, I think I need to mention one or two things more and then I will go ahead. So since I have some this very interesting identification between this unit tangent bundle and the group itself, then with the help of that several things which is happening here can be viewed inside the group PSL2R. So I am going to talk about a few of our 2-3 more actions on this space, and the way I will introduce is by means of what happens to the level of matrices. So let me put it in this way, that here the acting group is R. We do have a natural act, we can let act R on PSL2R in this way. So I am talking about 3 different actions. T comma G goes to G, it to the power t, t to the power minus t. This is a way. So, since R is abelian, so from the multiplying from the right is not creating any problem at all. So, this is an action of R on PSL2R itself, and by means of that identification, this action can be this action. So, in fact, actions of R called flows. This flow can be visualized geometrically inside this geometric object T1H, and I am sure that later on you will do some geometry course. So, that is called geodesic flow on the unit tangent bundle of the upper half plane. Similarly, we can talk about two other flows. One flow is just like this, 1S01, and of course, another kind of flow also we can to consider here. Instead of unipotent upper triangular, you act with a unipotent lower triangular matrix. So, these are called horocycle flows. So, for now these are just we just have their algebraic descriptions. So, algebraically this is just multiplying from the right by some abelian subgroup which is isomorphic to R, right. So, all these subgroups are isomorphic to R. So, algebraically on PSL2R things are just right multiplication by some abelian subgroup, but their meaning, their geometric meaning will much more, the geometric significance for what they mean geometrically will be clear once you view these inside the, once you view these flows inside this upper half the unit tangent bundle by means of this identification. There we will see that what actually is happening. You will understand the meaning of this. So, yeah, so those are quite interesting. So, these are, let me write it, horocycle flow. These are horocycle, one is stable, another is unstable, but let us not get into that. So, these are just, these are just algebraic descriptions of some interesting flows on this unit tangent bundle. So, but yeah, so it does not completely justify to mention them algebraically, but in order to understand them, their significance or their influence, the geometric perspective, the geometry should be revealed, but I am sure that you will later on encounter in any course in hyperbolic geometry or Riemannian geometry. So far I have just told you all those important flows purely algebraically. Okay. Now let us come to the action of so let k to n, and we do have GLNR. GLNR acts on the collection of all discrete subgroups of rank k of Rn, right. So, the GLNR acts on, in fact GLNR and SLNR acts on all discrete subgroups of Rn of rank k, okay. And we have already observed that this action is transitive, this action is transitive, the action is transitive, and what more, then in particular SLNR acts on the all discrete subgroups of rank n, that is the space of lattices, okay, the set of all lattices. So, is this action transitive? Actually no, because if gamma is a lattice and G is in SLNR, then it's easy to see that the covolume of G gamma and gamma are same. So therefore two lattices with different covolume cannot be in the same orbit. However, if they are having the same covolume, then of course they will be in the same orbit. So thus what we can do is we can consider the following subaction of this, that is the subaction of SLNR, the action of SLNR on Ln. So what is Ln? Ln is the unimodular lattices, the lattices with covolume 1. Okay. So the Sn acts from the collection of all unimodular lattices, and now this is transitive. And once it's transitive, it's interesting to know the stabilizer. So Zn, the standard lattice in of course in Ln, is a unimodular lattice. What is the stabilizer of Zn? So maybe I can leave it as an exercise, that instead as a direct verification. The stabilizer of Zn is nothing but SLNZ. Okay, that's quite easy to see. You can verify that. And now in view of this, we do have this identification SLNR, SLNZ. Now, so we do have this identification. So here also, like the previous one, a priori there is no, natural, there is no natural topology or anything on Ln, but in view of this, because this is in a nice quotient space, so we can topologize that, we can put a measure on that, and using that topology, using this identification, one can also put natural measures on the space of all natural topology, natural measure on the space of all unimodular lattices. So these are the advantages of having some space identified with some quotient. So this kind of things you will keep on visiting later on. Okay, now let's talk about actions on the space of forms. So most of the things have already been discussed, so I will quickly review. So as usual, we let V be a vector space over F, where not necessarily finite dimensional, Q, R or C, okay. And then we do have GL2, GL of V acts on all bilinear forms on V, okay. What about this action? Is this action transitive? Actually this action is not transitive, because for example, like of course if you just the zero bilinear form will of course now is not going to give us anything other than 0, but even more furthermore we can see something intelligent, that is if F is a symmetric bilinear form, then for any P, Pf is also symmetric, okay. So therefore we see that a bilinear form, a symmetric bilinear form with something which is not symmetric cannot lie in the same orbit. And in fact, let's look at the case when F is R. So let's take the case F is R and V is Rn. For example, then this will be quite clear to you. So as I said that a symmetric bilinear form, it has to be given by some symmetric matrix. So try to understand, as I said that this action is transitive, because of course if you don't bother about this zero bilinear form, even furthermore in general that anything lying in the orbit of a symmetric bilinear form is going to be symmetric. So let us look at the special case. So if F is a so if in this case let A be a symmetric matrix, so thus any symmetric bilinear form will be of this form, will look like this, symmetric. Then and if anything is and then what is going to be this fellow? So the matrix of anything which lies in the orbit of F. So if anything lies in the orbit of F, let me put it in this way, orbit of F, then its matrix must be of this form for some invertible matrix P, right. So anything which lies in the orbit of F under the action of GL and R, its orbit must be of this form, and from basic linear algebra we see that for any given A, its orbit so by applying P suitably we can bring its matrix to this form I some IR minus IL 0. So thus like the orbits of symmetric bilinear forms on Rn, they correspond to different signatures, okay. That follows from linear algebra, because each orbit consists a unique matrix of this form. All right. So here, so this is what here I would like to leave an exercise. If R is if F is C, so what happens then? So what happens? So regarding this, that for on Rn we have seen the what happens to the symmetric bilinear forms. So the question is what happens if what happens over C, that is what happens over C. Okay. Yeah. So if the field is C, then what can we say about what can we say about the orbits of symmetric bilinear forms? Okay, this is what the question means. And now from the action of bilinear forms, one can talk about the actions on the space of quadratic forms. So now from the action on the space of quadratic forms, let's now get into the action on the space of bilinear forms. Let's now talk about the action of GL and R on this set of quadratic forms. And so consider the action of GL and R. So let's make it simple. Let's stick to real case only. Action of GL and R on the space of all quadratic forms. All quadratic forms. Forms on Rn. So the first question is remember that a quadratic form is also given by this for some symmetric matrix A, and if you recall the action of PQ is defined like this, Q of P inverse X. So the matrix of this is also is a matrix of this form. Some basically it is, yeah. So the matrix is of this form. So analogous things also should hold here. Hence, I would like to leave as an exercise that find all the orbits, find the number of orbits, exercise on the space of quadratic forms, find the number of orbits. Exercise, find number of orbits. Okay, and of course another exercise is do the same. So earlier we have seen that the space of all non-degenerate quadratic forms, space of all positive definite quadratic forms, negative definite quadratic forms, indefinite quadratic forms, all these 4 important subsets are invariant under GLNR. So we do have actions of GLNR on them, on those spaces, on those invariant subsets itself. So therefore I should leave this also to you, do the same, and with that I will finish. The next lecture I will start from this. So here we just talked about the orbits only. In the next lecture we will consider the stabilizers under this action. Do the same, that is by same means find the number of orbits for non-degenerate, positive definite, negative definite and indefinite forms case. So GLNR acts on this collection, this collection, this collection, this collection. So we have 4 subsets, positive, definite, non-degenerate, indefinite. So for each of these cases find the number of orbits. Okay, yeah, the next lecture I will start from here. So here so far I have just discussed the orbits here, and from the next lecture I will start from the will start talking about the stabilizers under these actions. Okay, so I will stop here.